Good morning, everyone. The highest honor and award given by our society is the Claude E. Shannon Award, which recognizes consistent and profound contributions to the field of information theory. Shannon was a mathematician and engineer whose theories laid the foundation for the digital communications networks that lace the earth. His ideas and work have inspired our community for over 6 decades, and they continue to do so today. The recipient of the 2013 award is Dr. Katalin Marton of the Alfréd Rényi Institute in Budapest. Dr. Marton was born in Budapest. She graduated as a mathematician from the University Eötvös Loránd in Budapest in 1965. In 1969, she worked in the Institute of Information Transmission in Moscow. Since 1974, she has been working in the Institute for Mathematics, now the Alfréd Rényi Institute. She spent shorter periods of time at MIT and at Stanford University in 1979 to 1980, and at the University of Toledo, Ohio in 1986 to 87, and later on. She has worked in information theory, mostly in the theory of multi-user communication, partly in collaboration with János Körner. She then worked on problems in ergodic theory, partly in collaboration with Paul Shields. In the past 15 years, she has been working on problems in measure concentration. The work of Dr. Marton that I am most familiar with is her compact paper presenting a coding theorem for the discrete memoryless broadcast channel. This paper was published in the IEEE Transactions on Information Theory in May 1979. In this paper, she develops what is still the best inner bound on the capacity region of the two-receiver broadcast channel. The paper also gives what turned out to be an important outer bound, which was developed together with János Körner. As is the case for much of Dr. Marton's work, it took a quarter century for most researchers to realize how fundamentally important her results were and to catch up. The broadcast channel has received widespread interest in the last 10 years, since sophisticated devices and algorithms could be built that implement her ideas. For example, in the area of multiple antenna transmission, her theory guides the architecture of algorithms, and her work motivated several award-winning papers on broadcast channels. Another now classic result of Dr. Marton is a paper with János Körner on how to encode the modulo 2 sum of binary sources that appeared in the IEEE Transactions on Information Theory in March 1979. This paper was again way ahead of its time. It directly motivated recent award-winning work on lattice coding for wireless communications that is sure to be used in future wireless networks. I suspect that her other work, for instance on the blowing up lemma, will suffer a similar fate. And it would not be the least surprising if her subsequent work on measure concentration has practical impact many years from now. In this area, she discovered a new method to derive concentration inequalities through so-called transportation inequalities. In the words of Michael Talleyrand, this work is certainly a key moment in the history of concentration of measure. This fundamental contribution is entirely hers, much ahead of anybody else. Over her 40-year career, Dr. Marton has made consistent and profound contributions to the fields of information theory and mathematics. Dr. Marton, it is my great pleasure to invite you to give the 2013 Claude E. Shannon Award lecture.
I am thankful for the Information Society for the opportunity to give this talk about distance-divergence inequalities. So I am trying to keep this talk a simple-minded one, not with the most general definitions or theorems, because this is not really in the field of interest of the audience that attends ISIT conferences, and I apologize for that, but I haven't worked in Shannon theory for many years. And now, let me first explain my motivation, how I got to this field. And this was, the first motivation was to find a simple proof of the blowing up lemma proved by Alfréd, Gaussian, and Körner. They had in mind to find a way to prove strong converses in Shannon theory. And then also a motivation was my interest in Ornstein's isomorphism theorem, and actually what I used was a more precise version of Ornstein's so-called copying lemma. And the third thing that I could use from my experience in information theory was the so-called single-letter characterization method principle, and how to deal with these problems. And now, let us define the setting. We are given a metric probability space. More precisely, we assume that we are given X, which is a Polish space with the Borel sigma algebra. D is a Borel measurable distance on X. Q is the probability measure on X, and we will not really care about measurability problems. The notation that I first need to introduce, what I mean by enlargement or neighborhoods of set A is the kappa enlargement of set A, which I denote by A in bracket subscript kappa is the set of those elements of the space that are at most at distance kappa from the set A. Now, measure concentration is about, so to very roughly formulate the phenomenon of measure concentration is that for certain measures, and I emphasize that not for all measures, so this is somehow exceptional. For certain measures, it's true that if we enlarge a set A of not too small probability, according to this given measure, then if we enlarge it by a thin layer, then its probability dramatically increased. So there is a formula for that. So if QA is not too small, then the kappa enlargement has already a Q probability quite close to 1. And so it's important that, of course, that this kappa, for which this is true, can be overbounded in a non-trivial way, which means that we can take a neighborhood relatively small and still get a big increase in probability. Now, let me explain how the concept of enlargement of a set is connected to distances between sets. So this is explained in the figure that I am showing. So above this picture, there is this formula that which is a triviality. So the distance between A and the complement of its kappa enlargement is just kappa. So this phenomenon is illustrated by this picture. Here we have A, and the blue region is the complement of the enlargement, and it's clear from the picture that the distance between the red set A and the blue set is just kappa. So by this formula, I explained on the previous slide, we can give the following equivalent definition for measure concentration. So a metric probability space X, D, Q satisfies the measure concentration property if there is a function kappa mapping positive real numbers to positive real numbers with the property that for two sets A and B in the space, their distance can be overbounded by using their probabilities QA and QB, and we have to take an appropriate function of these probabilities and add them up. So this formula can be an alternative to the previous definition, and again, so kappa has to be such that it can be overbounded in a non-trivial way. So in this talk, I will speak about what's called sub-Gaussian or sometimes Gaussian measure concentration, and here we have the following form of kappa of epsilon, that it is a constant times the square root of logarithm of 1 over epsilon, and the constant, of course, depends on q. So a measure satisfies a Gaussian measure concentration inequality if the definition holds with kappa epsilon of this form equivalent. So if kappa can be expressed by epsilon, then epsilon can be expressed by kappa in this way. So epsilon of kappa is e to the minus kappa divided by this constant to the square, and this is why it is called Gaussian concentration or sub-Gaussian concentration. And the equivalent definition is that the distance between two sets is this constant dependent of q multiplied by the sum of two things, namely of logarithm of 1 over QA plus the square root of logarithm 1 over QB. Now, measure concentration is mostly or very frequently used in product spaces, and the first example I consider is for product spaces, and the distance that is called Hamming distance, and so it's familiar for everybody. So let xn be the nth power of a Borel space. I emphasize that so everything makes sense if x is not discrete. So here I wrote the definition of Hamming distance, which you know. This is my notation for an n-length sequence consisting of x1, x2, and xn. So the sequence is denoted by x superscript n. And let q superscript n be a product measure of qn of not necessarily identical factors. And then if we take neighborhoods with respect to the Hamming distance, then we have the following inequality. So the product probability of the neighborhood is smaller than 1 minus an exponentially small quantity, because if you look at this formula, which is somewhat complicated, but then there will be given a simpler formula for that. So then, it turns out that it's in the exponent, the main term is kappa square multiplied by n and multiplied by 2. So the formula above just repeats the previous formulas, and here you can see an equivalent definition of the previous one, and I think this is much more transparent and understandable. It means that the Hamming distance of sets A and B, so here nothing is required about their individual probabilities, so we have a bound of the form of a sum, where the first term is you take the logarithm of the measure of A divided by 2n and take square root, and then add the same thing for the set B. So again, I think this is a much more understandable form of the above formula, although maybe it's not at once apparent that they are equivalent, but they are. So thus, for Hamming distance, this kappa epsilon is the square root of 1 over 2n multiplied by logarithm of 1 over epsilon. So this is really Gaussian concentration. Now the second example, which the previous example at first was proved by the upper inequality was proved by McDiarmid in I think 1998. No, earlier, 1989, yes, and the equivalence was found later by myself. No, so this was the first example with Hamming distance. Now let's consider the second example, Euclidean distance. And what follows was proved by Talagron in a paper in 1996. So we consider the n-dimensional Euclidean space with Euclidean distance and consider a product density, and each product, I must say that in the continuous case, I just write the same letter for distribution as for density. So in this formula, Qn is a density. It's the product of densities, and each density has this form with the following assumption on the exponent, that it is strictly uniformly convex, which means that its second derivative is bounded from below by a constant r, which doesn't depend on x. So then what Talagron proved is the following, that the distance, Euclidean distance between two measures with respect to such a product measure, so the Euclidean distance between two sets can be overbounded by this formula, which is very reminiscent of the one for the Hamming case. Just here in the bound we have this constant that lower bounds the second derivative of the exponents, and it doesn't contain the dimension, which is essential and which is characteristic of Euclidean distance and in a way of some other distances. Here I just repeated what was on the previous slide, and for Euclidean distance of the above, for the Euclidean distance and for product measures with factors satisfying the condition of that they are strictly uniformly log concave, we have this expression for kappa epsilon square root of 2 over rho, and this rho is this lower bound for the second derivative, and is multiplied by logarithm of 1 over epsilon, and this bound and this expression is independent of the dimension. So now I am proceeding to distance-divergence inequalities, which is a way to prove measure concentration. So let me define the setting. We denote by P of x the set of probability measures on x, and Q is a distinguished element of Px. So Q sometimes denotes a density and not a measure. A basic tool is the following: the couplings of two given probability measures. So let me just come back to this. I forgot to emphasize that the Q is a distinguished element of the set of probability measures. And so the theorems are always formulated for one specific Q. Now let us define Wasserstein distance, that is distance between measures, and for this we first consider the set of couplings of two given measures PR in the set of all probability measures, and this set consists of all couplings of P and R, and coupling just means that a joint probability distribution P on well, so here so joint probability distributions on the product space, and this joint distribution is can be considered as the joint distribution of a random pair Y of Z. And so a coupling is such a joint distribution with marginals P and R that are the originally given distribution. So this is how distances, how Wasserstein, how couplings are defined. And now these couplings are used to define what is called Wasserstein distance, although it was earlier than Wasserstein, used by many mathematicians. So this is the following. This is so I give the definition that depends on a parameter beta, but so the best thing is that you consider either the case beta equals 1 or beta equals 2, and I just gave a definition to make the two definitions into a united framework. So what we do is we take the couplings between these measures, or the couplings, and for a given coupling we take the expected value with respect to this coupling of the distance of the random variables Y and Z, and we take the beta's power of this distance, and then after taking the expectation we raise it to power 1 over beta. So this is basically an LP L beta type thing. And again, the infimum is taken for the couplings with marginals P and R. So this WBPR is called the Wasserstein distance of P and R of order beta. And it can be easily seen that W beta is indeed a distance on the set of measures, although it can, so except that it may take the value infinity. I think I just repeated there the above definition of Wasserstein distance, and then let's proceed to the simplest example, which is the case when the distance that we consider on the Borel space is Kronecker's distance, which I denote by delta. So this is again familiar to everybody, and it turns out that the corresponding Wasserstein distance is just the total variation distance between P and R, And it's not completely trivial, but easy to see, and I think it was, Dobrushin already used this equality. I am not sure whether it had been used before. Anyway, so it's an important thing that variational distance can be sort of as a Wasserstein distance defined by the distance, by Kroneker's distance. Here are all more or less clearly equivalent formulations. Now, distance divergence inequalities are about estimating Wasserstein distance by information by a constant times by informational divergence in some way. Here you have the definition of informational divergence of a measure P with respect to Q, and this Q will always be that fixed distinguished element of a distinguished probability measure. Now, so a distance divergence inequality means the following. We say that Q satisfies a distance divergence inequality of order beta with constant rho if the Wasserstein distance of order beta between P and Q can be overestimated by this expression square root of 2 over rho multiplied by the divergence. And this should hold for the fixed Q, but the other measure should be any measure. So again, the most important cases are beta equal 1 or 2. Again, this is a repetition on. So I gave a repetition of the previous definition, and now let's proceed to the simplest example, which is Pinsker-Chisar-Kullback inequality. So the distance, the Wasserstein distance that we take here is the total variation distance, which is a Wasserstein distance, as I told before, and it can be overbounded by the square root of, so this formula, this is well known, so this inequality is well known, and this holds for, so at first I told that it should be varied for the fixed Q and for any P, but in this case it holds for all P or any P and any Q. So the distance divergence inequality holds the same constant rho equal 4 for every Q, because this 1 over 2 should be 2 over rho, and this is from where this rho equal 4 comes. Now, let's proceed to Euclidean spaces. I denote by W2 the Wasserstein distance. So this is now on the measures on the real line, and we consider their Euclidean distance, and W2 denotes the corresponding Wasserstein distance. And then And then, so here is the definition that I explained in words in the last sentence. Now, I am turning to Talagran's theorem of 1996, which is somehow the same thing as the Pinsker-Kullback inequality, but for Euclidean distance, which makes it much more difficult to get. And this is the following. So first I explain it on the real line. Let's take a density with a strictly uniformly, so let's take a strictly uniformly log concave density. This is here. So this is the expression that is log concave. The most important example is the normal density, Gaussian density. And Talagran proved this inequality that this Wasserstein distance that corresponds to Euclidean distance can be overbounded by this expression where this rho is the same as the lower bound for the second derivative. The proof of Talagran's theorem based on the existence of and the calculations of the unique monotone map T that takes the measure that takes basically any measure P on or any density P on R to the measure to a given measure Q, provided both are absolutely continuous. So it can be written like this. Maybe this is not familiar to anybody, but such a map exists, and this was used in Talagran's proof. Now, a very important thing is that a monotone map taking a given density P to the density Q exists also on Rn. This was proved in different forms by basically the main two persons here were Rényi and McCann. So a monotone is not so easy to explain in high dimension, but it's basically that it's the gradient of a convex function. So that's what monotonicity means. And by this more general theorem, the one-dimensional Talagran theorem can be proved also in the n-dimensional Euclidean space. So assume that we have that Q is strictly uniformly log concave density on Rn, which means that the Hessian of Vx is bounded from below by rho times the identity with a positive rho. And then we just have the inequality that formally looks the same as the one-dimensional inequality, except that here this W2 should mean that Wasserstein distance derived from the n-dimensional distance. So this inequality has many proofs. I will not go into that. Here I am proceeding to the first key observation that connects measure concentration and distance inequality and distance divergence inequalities. This is the following: that if we have a metric probability space and W beta D denotes the corresponding Wasserstein distance, and if we have this distance divergence inequality, so this is Wasserstein distance overbound by divergence, then this inequality implies this form of what I call measure concentration. And here, this rho is the same as this rho. Let me take a few moments to explain, to outline the proof. So the idea is to replace sets by measures. So we replace the set A by the measure which is the restriction of Q to A. So that, and this will be denoted by P, and the similar thing for B, the restriction of Q to B is R. And then it's easy to see that the distance between these two sets is smaller than the Wasserstein distance between the corresponding measures. So these are the restrictions of Q to those sets. Now, by triangle inequality, this distance can be overbounded by two distances, distance of P to Q and from Q to R. And then we apply distance divergence inequality, so we get to this last line. And this formula is just the repetition of the previous one. And now the second step is just to observe that the ratio of P and X is 1 over the probability of A. So here we use that P is the restriction of Q to A. So this is true P almost everywhere. And therefore, the divergence is exactly the logarithm of 1 over the probability. And divergence between P and Q is just a logarithm of 1 over Q, and the similar holds for beta, for B, and this completes the proof. Now, as I told, we mostly, not mostly, but frequently need measure concentration in product spaces. So to handle product spaces, we need special measures on product spaces, and here is a definition. So if originally we had a distance d, then on x, then we can define a distance on the nth power by this formula. So this is very similar to the definition of Euclidean distance, just so here we take the distance d in one dimension, and in Euclidean distance this would be the one-dimensional Euclidean distance. So in this way we get Hamming distance from Kroneker's distance with beta equal 1, and we get Euclidean distance from one-dimensional Euclidean distance with beta equal 2. And now we also extend Wasserstein distance to the definition of Wasserstein distance to product spaces. And it's done in the following way. So we have defined a distance on the product space Xn, and then the definition is the following. So it depends on n, on the original distance on d, and the parameter beta. And so we take the couplings between Pn and Rn. Such a coupling is denoted by P, and by these couplings we define from the distance on the product space the Wasserstein distance between measures on the product space. Now this looks somewhat complicated at first sight, but very logical. But so this is so here arises a difficult problem: how to find good couplings between two distances that are on a product space. So sort of we consider that we can make good couplings between measures on the original space X, but but to find such couplings from these in product spaces is difficult. And we usually cannot find the optimal coupling, but just one that is good enough. So the second key observation that makes distance divergence inequalities useful is the following, that it tensorizes, which means the following, that let us assume that we have a product space Qn on the product space, and let us assume it has factors Q sub I. And let us assume that we have a distance divergence inequality for each Qi separately. This is what is written here. And then we can prove that for the product measure Qn, we have again an inequality of the same type, which contains the same row, but it depends on n, and how it depends on n, that depends on beta. And so for Hamming distance, here this factor becomes just n, and so we have the constant of distance divergence inequality equal to 4 over n, the same as for Pinskers inequality. And for Euclidean distance, if we consider n-fold product measures which satisfy distance divergence inequalities with the smallest distance-divergence inequalities, then the product measure will have distance divergence inequality with the smallest of these constants. And then there will be no dependence on n, which, so as I told, is a feature of Euclidean distance. Now, so the proof, I will not really describe the proof. So the proof is basically based on how to construct a good coupling between a measure Pn, which may not be a product measure, and Qn, which has to be the product measure, from couplings in one dimension. I will not give the details. Now, let me explain. Let me cite two theorems that express that somehow distance divergence inequalities capture something really essential. These are inequalities of the large deviation type. So the first one I would like to mention is a theorem of Bobkov and Goetze from 1999, and it says that in any Borel space, any metric Borel space, the following two statements are equivalent. The first statement is that we have a measured concentration of order 1. This is how it looks with some constant rho. And the second one is a large deviation type, or let us rather call an inequality for the moment generating function. So, this statement, this inequality is equivalent to this one. So this basically says, again, so this inequality is equivalent for all p is equivalent to the following, that this inequality for the moment generation function is valid for all Lipschitz functions with Lipschitz constant 1. And I think it's it's not only for t larger than 1, so for any t. So I think this is an important thing, and let me explain it a little more. So Bobkov and Goetze actually proved, so it's not stated in their paper, but it follows from their proof that for any fixed function of f on x, I mean a real valued function, if we take the moment generating function, and we have for that f this estimate for the moment generation function, then it means that for any other p, we can bound the difference between the expected value of f with respect to p and with respect to q by this expression. And this is valid for all p. And I think this is this is maybe even more important than the previous theorem. And somehow it explains, perhaps it explains, I'm not sure, it expresses, it is the key how the method of distance-divergence inequalities is connected to the entropy method, of which Gábor Lugosi will speak tomorrow. I'm not sure. The second theorem of the type of the large deviation type is more complicated. That's for Wasserstein distances of order 2. So let us consider a metric probability space. And we denote by, so Q is the measure, and let Qn be the nth power of Q. So if we have on the original space x dq this distance divergence inequality, of course for all p, then we have this inequality of the type of large deviation for the product measures that come from Q. So this means that the probability that for a function f, which has to be Lipschitz with coefficient 1, so for a function f, the probability that the value of the function exceeds its expected value plus something is in a Gaussian way small, depending on this R. So now I would like to, I don't know how much time I have. 5 to 10 minutes. Thank you. So until now, I spoke of the product measures, but we can get results for, so being a product measure can be replaced by being a weakly dependent measure. And the first example is, the simplest example of this is a Markov chain. So, and a Markov chain that is contracting, which means that if we start from two different states, then in the I think this. So this here should mean the transition probabilities. I think the notation is a little confused. After using the Markov kernel, the total variation distance decreases. So if it was, if x and y were equal, then of course the total variation distance here will be 0. But if they were not equal, then it will be strictly smaller than 1. And now let us define for the product space this distribution, which is so we take a distribution on to start, and then we multiply all the transition kernels. And then we have the following inequality for this measure, which is Markov. So, and we use, so here the delta means that we are using Hamming distance. We get the same inequality as for the independent Qn, just multiplied by 1 over beta. So it's just a constant time worse than what we had. So I think here I skip a few things. So I would like to say a few words about measure concentration for Gibbs measures. So we again consider a product space with a measure Qn on it. And we shall later formulate a condition that provides for weak dependence, but it's a rather restrictive condition. Let Xn denote the corresponding random variable. And then I use this notation. So if I have a sequence of length n, then by bar y sub I, I denote the sequence that I get if I omit the ith coordinate. And the important thing is what is called local specification for Q, which is the conditional distribution of the ith coordinate given all the other coordinates. So these are called local specifications. And so what I call Gibbs measures is not really the standard definition, but here I define Gibbs measures just simply, so when a measure Qn is defined by its local specifications, then I call it a Gibbs measure. And there is a very often used condition, Dobroshin's uniqueness condition. I think many people know it, and so this refers to the following, that if we start from two different sequences, bar y that is case coordinate omitted, z and z bar k. And if these two sequences are such that they only differ in the ith coordinate, then the assumption is that the total variation distance between the transition measures is overbounded by these numbers that depend on a and k. And if we put together these numbers into a matrix and put zeros in the main diagonal, then then its bound L infinity is strictly smaller than 1. So this is a very restrictive condition, but we assume that no. Maybe yes, so maybe the last thing I mention it will be this theorem by Liming-Wu in 2006. So if Qn satisfies, so we consider a Gibbs measure, that is one that is given by these local specifications, and if the local specifications satisfy Dobroshin's uniqueness condition, then we have this distance-divergence inequality where here in the denominator is a positive number because we assume that this norm is strictly smaller than 1. So my time is over, and thank you for your attention.
Thank you very much, Dr. Marton. Perhaps we will take one quick question if there is one. There's someone waving right at the back over there.
Well, I cannot hear anything.
Yeah, he has to get the microphone.
I see.
In the Euclidean space example, do you have an intuitive explanation of why kappa of epsilon is inversely proportional to the lower bound on the second derivative of vi?
No, it's not at all intuitive. It's just so. So one has to go through the proof, and then you can see that this is so.
Thank you.
Okay, on that happy note.
So at least I cannot give any intuitive explanation.
On that happy note, we'll thank Dr. Marton again for inspiring.